My name is Monet Bichner. I study molecular and cell biology. I have wanted to go into a biology field for a very long time. And as part of my studies, I do quite a bit of chemistry. So I'm going to be walking you through the KZN June 2018 chemistry paper. And just as a bit of housekeeping before we get started, you'll need a copy of the periodic table. If you don't have one already, there is one attached to this paper that you can use. You're going to need a calculator, and you're going to need a notepad and some stationery or whatever medium you prefer to take your notes with. So without any further ado, we can get started. So question one in a physical sciences paper is multiple choice. When you go about multiple choice, especially in chemistry, you can usually narrow it down to two options at least by just doing process of elimination. All right, so let's get into this first question. Which term describes the ability of metals to stretch into thin wires? Is it A, brittle, B, ductile, C, malleable, or D, tensile strength? Does anyone have an answer? Maybe you want to put it in the chat. Okay, Sinatando says D. Um, okay, so when you say D, are you looking at the word stretch and associating that with tensile? Is that the reasoning behind your answer? Because unfortunately, D is incorrect. Um, let's see if there are any answers coming in. C, carabo. Okay. Malleable. Okay. So these are some term definitions that it looks like you guys need to maybe brush up on a little bit, okay? Because brittle means it is easily broken by blunt force. So if you think about something like glass or porcelain, those are brittle. Malleable is the ability to be hammered into a shape. So metals, when hot, are malleable, but that's not the definition that we're looking for. And tensile strength is the ability of a material to hold up well when it's being stretched, which is still not the same thing. The ability to be stretched into wires is ductility. So ductile is the term that we're looking for here. Okay. The next question, they ask about silicon, the element silicon. Would you classify silicon as a metal, a non-metal, a metalloid, or a transition metal? How are you guys feeling about that question? What do you think the answer is? Okay. So I'm seeing some B and some C. C. Okay, let's have a look. Okay. I'm seeing lots of C for non-metal, but if you, I don't have a picture of the periodic table in this, which I probably should, but the division between metals and metalloids in period 3, so row 3, runs between, so if you look at the right-hand side of the periodic table, it goes aluminium, silicon, phosphorus, okay? Aluminium is a metal that you all should be quite familiar with. It's used a lot in construction. So this we know is a metal. And phosphorus um, is definitely a non-metal. Okay. Whoops. Phosphorus is definitely a non-metal. So silicon in the middle there is actually the first metalloid on the periodic table. All right. It can behave as a metal or as a non-metal. Silicon we use in computer chips, so like CPUs and GPUs and those sorts of things. But it can also form glass, which is, for all intents and purposes, functions like an ionic compound as silicon dioxide. So silicon is very definitely a metalloid. All right, so it is B as well. Okay. Now, this question this is some like really, really early term one stuff. And you've probably maybe done this in primary school as well. Solid carbon dioxide turns directly into a gas at room temperature. This process is called ... Let's see some answers in the chat quickly. Okay, I'm seeing D, A, B. Oh, we're divided here. Okay. A. Okay, so far the favor seems to be for A. 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 Okay. Okay, now the A's are coming in strong. Let's see. So, the process of boiling, does anyone want to put into the chat what the phase change for boiling is? So boiling which is A, which is what a lot of you said, and I can see why you might say boiling, but boiling is from a liquid to a gas, okay? Deposition is from a gas to a solid. Sublimation is a solid to a gas, and evaporation is a liquid to a gas. Okay. If you drew this out, so you had solid, liquid, gas like this, liquid to a gas that way is boiling. This way is condense. This way is freezing. That way is melting. And then these two big jumps that jump straight over being a liquid, this way is sublimation. And you guys are free to take a screenshot if you need. And this way is deposition. All right. So, armed with that little bit of information, the answer is once again B. Oh, sorry. C, it's sublimation. Sorry, my mistake. It's sublimation. All right. If we carry on to question 1.4, the type of bond where both the bonding electrons come from the same atom is described as A or an. Okay. So before we even start answering this question, can somebody please into the chat put for me what is the interaction that leads to an ionic bond forming? Jessica, we are busy working through a past paper, so I am revising, but I'm not reteaching. Anybody want to put the definition of an ionic bond? My pleasure, Jessica. A non-metal and a metal. Thank you. Tepaune? I'm not sure how to pronounce your name. I'm sorry. Okay. So this is a metal with a non-metal. Whoopsie. Okay. To a non-metal. Okay, so a metallic bond is a metal to a metal, usually to itself. Okay. And then a covalent bond we know is a non-metal to a non-metal. It's all to a non-metal. All right. But what is the difference between these two? The difference between a dative bond and a covalent bond. I'll give you a hint. It's a little bit like the difference between squares and quadrilaterals. Yeah, Leonese, that is a very nice answer. Ionic bonding involves the attraction of oppositely charged ions. I really like that answer. It's really nice. Umalima, I do think we are making the recordings available. I'm just not 100% sure where. Dative bond involves three atoms. I disagree with you there, because you can form a bond between quite a lot of atoms, but it very much still is a difference between whether they're metallic or non-metallic and in what ratio they're combining. So no, a dative covalent bond is, oops, there I gave the answer. Haha. Okay, a dative bond is not to do with the number of atoms. Okay, a dative bond is a type of covalent bond. All right. A dative bond is where a lone pair of electrons gets involved in the bonding. So, for example, carbon monoxide makes a dative covalent bond. Okay. Oxygen has two lone pairs and two bonding electrons normally. And carbon normally has four um, bonding electrons. Okay. But now, if you, oops, I have no idea what I just did. Sorry. If we were to say, okay, well, oxygen can bring its two bonding electrons here, and carbon can put two of its bonding electrons there, that still does not solve the problem. So what ends up happening is that carbon shares all of its electrons. So carbon actually shares all four of its electrons, and oxygen puts its two into that bonding arrangement as well. So it forms this triple bond. But these electrons are both from carbon. There is not a pairing up the way that there is for those. And that is what they're describing here, where both the bonding electrons come from the same atom. All right. So the answer that we're looking for is B. It's the dative bond. Okay. So dative bonding is a subset of covalent bonding. On to the next question, unless there's a question from anyone in the chat. Thanks, Wadabile. I see you shared the webinar links. Awesome. Okay. Sure, Leonie, you're on a roll here with these definitions. Keep it up. Okay. So the next question asks us about which of the following reactions can be classified as redox. Now, redox stands for reduction, oxidation. Okay. And when you're doing anything with reduction oxidation reactions, you should remember the little handy mnemonic oil rig, like those enormous things they put in the sea to drill oil. It's called an oil rig. But what it stands for here is oxidation is a loss and reduction is a gain. But of what exactly? And all of this is speaking about electrons. All right. So when you're doing a question where they ask you to identify the redox reaction, what you do is for every single element on the product side and on the reactant side, you need to work out what the charge on that element is. So when zinc is a solid, it's bound to itself in a metallic bond and it has a charge of 0. In hydrochloric acid, the hydrogen assumes a positive charge and the chlorine assumes a negative charge. In zinc chloride, Zn is charged 2 plus and chlorine is charged 1 minus. And in hydrogen gas, the hydrogen is neutral. Okay. Here, the potassium is 1 plus. Oopsie daisy. The potassium is 1 plus. The chlorine is 1 minus because it's an ionic bond. The silver is 1 plus. And the nitrate is 1 minus. Here, the potassium is 1 plus, the nitrate is 1 minus, the silver is 1 plus, and the chlorine is 1 minus. Here they've given you the charges on the two reagents already, the 2 plus and the 2 minus, and here they keep those charges, 2 plus and 2 minus. All right. For zinc chloride, we've already said the zinc assumes a 2 plus charge and the chlorine has a minus charge. Calcium sulfate. Sulfate is always charged 2 minus, so calcium here is 2 plus. Zinc sulfate is 2 plus and 2 minus. And calcium chloride is 2 plus and 2 times 1 minus. Okay. So if we look here at gaining and losing electrons being the definition of a reduction oxidation reaction, when you are looking for which one is an oxidation reduction reaction, you are looking for one where one product or where one reagent gains electrons, and where one reagent loses electrons. Okay. Here they're not asking you to identify which one. So it is sufficient to look at which systems or the elements change charges. All right. So here we have zinc with a neutral charge, and here we have zinc with a 2 plus charge. So this is well on the way, right? Here we have a hydrogen with a positive charge, and here we have neutral hydrogen. So A is very much a redox reaction. But let's quickly go through why it cannot be B, C, or D. In B, the potassium stays positively charged 1 plus throughout, so it's not gaining or losing anything. Chlorine stays 1 minus throughout, nitrate stays 1 minus throughout, and silver stays 1 minus throughout. So there is no gaining or losing of electrons in B. Here, copper 2 plus stays copper 2 plus, and oxygen 2 minus stays oxygen 2 minus. In D, Zn2 plus stays Zn2 plus, sulfate stays negatively charged 2 minus, calcium stays calcium 2 plus, and chlorine stays 1 minus. So it has to be A by process of elimination as well. Is anyone a little bit confused about how that happened? Oh, sorry. I didn't catch the... Okay, I'll go over it again. So, let's start right back at the beginning. They're asking you which one of these reactions can be classified as a redox reaction. Okay. So, the definition of a redox reaction is that one reagent has to gain electrons in the process, and one element, let's say one element, has to gain some electrons in the process, and one element has to lose some electrons in the process. Is that clear to everyone? Sorry, I'll try to speak a little bit louder. It might be an issue with my mic though. Okay. Unati, if that is not clear to you, then maybe you should revise the definitions in that section a little bit, because that is the definition of a redox reaction, where you have atoms or elements gaining and losing electrons. That's just a definition, okay? Then, once you have said, okay, well, for a redox reaction to take place, you need to lose electrons from one element and gain electrons on another element. Then you can go here and you can look at, well, where has there been a gain or a loss of electrons? Do we all agree that electrons are negatively charged by nature? Okay, amazing, cool. So, if electrons are negatively charged by nature, right? So electrons equals a negative charge. If we take away electrons from something, has it become more positive or more negative? If we take electrons away, okay. Okay, I'm seeing there's some confusion here. Okay. So, Sinotando, Zn does not have 0 electrons. Okay. Zn has a neutral charge, which means it has the same number of protons as electrons. Okay. For zinc, that is, just find it on the periodic table. Second. It is 30. So in this situation, zinc has 30 protons and 30 electrons. So if you have plus 30 and minus 30, that gives you a charge of 0. Okay, so that's how we got to 0. It does not have 0 electrons. Okay, so if we are gaining electrons, things become negatively charged. And if we are losing electrons or taking away electrons, things become positively charged. So when we are trying to identify a redox reaction where we are gaining and losing electrons, something should become more positive and something should become more negative as the reaction goes on. So from being a reagent on the blue side to being a product here, that element needs to change charge. Is that clear? Okay. Okay. So if we are looking for something that has changed the charge, all that we are looking for is where something has a different charge, so the same element has a different charge from the reactant side, from, from the reactant side to the product side. All right. So for this question, this zinc that goes from neutral to positive and this hydrogen that goes from positive to neutral are what we're looking for. Does that clear it up a little bit for everyone? Do we have less confusion? Yes. Okay. Uh, so redox reaction is when other elements lose electrons and other elements gain electrons. Yes, that is correct. Usually they are exchanging them. So one loses them by giving them to the other one. Okay. Someone's asked me to repeat the last statement. When you're looking for a redox reaction, so if they ask you which one of the following can be classified as a redox reaction, what you are looking for is the same element, so in this case it's zinc and hydrogen, that has a different charge from the reactant side of the reaction, so before the arrow, to the product side of the reaction, after the arrow. So here, zinc has a 0 charge, and here it has a 2+ charge. Here, hydrogen has a 1+ charge, and here it has a 0 charge. So both of these have changed charges going from the reactant side to the product side. Here we went from positive to neutral, and from zinc we went from neutral to positive. Okay. Umalema, I've been spending half an hour on 5 questions, which is quite slow if you think about how fast you have to actually write the paper, but I will try and slow down. Okay. The energy released when an electron is added to an atom or a molecule is called. Okay. So all that they are asking for here is a definition. This is a definition that is on your definition sheet that you have to know, and all they are asking you to do is match it with a term. Okay? So the definition for ionization energy, I have it a little bit further down in my presentation. Let me just find it. The definition for ionization energy is the energy needed to remove electrons from a mole of atoms. Okay. So that's ionization energy. That definition does not match. All right. So it can't be ionization energy. The definition of what's the next one? Enthalpy change is the change in the energy of the reaction from reactants to products. So that doesn't match. This is the definition for electron affinity. So again, it's B. There's a lot of B in this paper, in the multiple choice. It's not always like this where they're favoring one letter for whatever reason, but in this paper they did. Okay. Is that clear to everyone? That's just a definition to learn. You want to copy the redox reaction? Can you take a screenshot just to make it a bit quicker? But yes, you're welcome to take a screenshot. Okay, I'm going to give a couple of seconds for people to screenshot if they need. Going, going, gone. All right. Then, the separation technique most suitable for the separation of an oil and water mixture in the lab is, does anyone want to venture a guess? You're welcome. Ooh, okay, so we have one A and one B. One B, another B, another B. Okay, let's have a look. Okay, so if we draw out a mixture of oil and water, so say here we have a test tube, and in the bottom here we have some water, and floating on the top of that water we have some oil. Okay, that's the setup that we have. Okay, that's this oil-water mixture that they're talking about. Okay, now, on what basis, and this is what you should study when you're studying these separation techniques, okay? On what basis, on what chemical property are they separating substances, okay? So, chromatography is separating substances based on two properties, okay? A, it's separating them on their charge or their polarity. And B, it's separating them by molecular mass. That's chromatography. Magnetic attraction is what it says on the tin. It is separating substances based on magnetism. Okay, so this is only useful if you are separating a mixture of iron, cobalt, or nickel. Anything else, this is not going to be useful. So here, it'll always be most useful for iron, cobalt, and nickel. Those are your magnetic metals. And fractional distillation is separating things based on their vapor pressure. And their volatility. It's a horrible word for me to say. Based on whether they are volatile or not. Okay. So, decanting is separating liquids, very specifically liquids, a bit clearer, liquids based on density. Okay. So, there is not a difference in charge or polarity between oil and water. Okay. They are both, well, They do have a difference in charge, but you're going to have a very hard time conducting chromatography on this. Okay. Um, Purely because they don't actually mix. Okay. Then magnetic attraction, neither of these are magnetic. All right. Just by virtue of them both being non-metals. And fractional distillation is based on the volatility. Now, oil is not going to come off in fractional distillation, and it's trapping the water underneath it. Okay, do you see? So if you try to do fractional distillation here, you would be wasting your time because the water, which is the more volatile substance, is trapped underneath the oil. Okay, the water cannot evaporate because the oil is on top of it. So the only option that you're left with is to decant. Okay. If you want to, I highly recommend you try this at home. This is one of the chemistry experiments you can actually try at home. Is take some oil, take some water, and pour them into a glass, okay, or a cup or whatever you have on hand, and you will see that the oil floats on top, which means that the oil has a very low density compared to water. So this is a low density. Okay, that's the symbol for density. I am very bad at drawing it. And it looks like a weird P. There we go, that's better. And water has a high density. Okay. So this decanting is essentially to pour something off. Okay. So it would be like if you took this little test tube that we drew and you just tilted it until all the oil had run off and you were left with just the water underneath. Okay. And that you can try that at home. That's an experiment you can do at home. Okay. If anyone wants to take a screenshot, I'm giving you 10 seconds. All right. Let's move on to the next question, which is starting to get into the short questions. This one is about states of matter. Okay. This question does ask for some definitions. All right. So what I've done is rather than writing out the definitions every time, I've just put them on the slides because the definitions I cannot teach you, you have to learn. Okay. So temperature is the measure of the average kinetic energy of the particles, and boiling point is the temperature of a liquid at which its vapor pressure equals the external pressure. All right. So in this situation, they give you this cooling curve. Okay. Before we even look at the questions, we can do quite a bit of analysis on this nice little cooling curve that they've given you. Okay. The first thing that you always look for in a cooling curve is a plateau, a bit where the line is flat and parallel to the x-axis, okay? So you look for your plateaus because a plateau on a cooling curve or on a heating curve, because if you flip this around, you like mirror it along that line, that's just a heating curve. It's the same thing. A plateau is a phase change. Okay. So once you've found your two plateaus, now you know, okay, well, if we are cooling and we are losing energy, which way are we going? Are we going from a gas to a solid, or are we going from a solid to a gas? Broadly speaking, yes, there is a liquid in between there, but which way are we going? Are we starting with a gas or are we starting with a solid? You guys can put the answer in the chat. You can just put G or S. Okay, gas. Gas to solid. Okay, gas, gas, gas. Getting lots of good answers here. Yes, we are absolutely 100% starting with a gas. Okay, so this phase change has to be gas to liquid. Okay, and then this phase change has to be liquid to solid. Okay, so now you can label either side of these plateaus. So this side here, this first bit, it's a gas. Here, it's a liquid. And then this part they haven't labeled, but you can label it for yourself. Here, it would be a solid. Okay. So when you get a heating or a cooling curve, before you even look at the questions, put this on the graph for yourself. Okay. The next thing that you can read off is because you know where these phase changes are, you can interpolate them back to the y-axis to get the temperatures at which they happen. All right? So here we know that this change, the gas to liquid change, happens at 95 degrees Celsius. Okay? So is 95 degrees Celsius the boiling point, BP, or the melting point, MP? You can put your answers in the chat. Okay. Yeah, it's the boiling point. Uh, guys who are saying they don't understand, please be a little bit more specific. Okay, where is the melting point? I'm going to show you now. Okay, so 95 degrees is the boiling point. So the transition between a solid and a liquid is the melting point, right? The freezing point and the melting point are at the same temperature. So this would be the freezing point or the melting point. It's the same thing. Okay. In this case, it's technically freezing because it's going liquid to solid, but it will melt at the same temperature. All right. I can leave that there. It's fine. So here, 5 degrees would be your melting point. Okay. Is there anything I should clarify about how to read a heating curve or a cooling curve before I move on to the questions? Uh, 5 degrees is the melting point because it's the transition between the solid phase and the liquid phase. Okay, one more time, what? I cannot repeat the whole explanation. Otherwise, we will be here all night. Okay, the freezing and the melting point. Okay. So, if I was to turn this graph around, right, and draw exactly the same thing, but starting at the bottom and going up, would you agree with me? Okay, ignoring the blue curve now, let's just talk about the pink curve. Would you agree with me that this plateau on the pink curve would be melting because it would be going from a solid on this side and a liquid on this side? Do you agree with me then that this would be the solid to the liquid, so melting? Okay. You don't understand the whole topic. You don't understand phase changes. Oh, okay. Um, unfortunately, I'm not reteaching, so it might be better to speak to a teacher or maybe book a tutoring session, because unfortunately I can't um, reteach the whole topic. Okay. Tandeka is asking, do the intermolecular forces break or bond during a cooling curve? Okay. Intermolecular forces are not bonds, Tandeka, but intermolecular forces are being, during a cooling curve, they are being formed. Okay. So during a cooling curve, you're going from the gas where there is very little interaction. Because remember, if you draw a particle diagram of a gas, they're all sort of scattered around, right? They're not interacting with each other. Then, if you draw a liquid, they're all sitting on the bottom here, and they are interacting with each other. So there is slightly stronger intermolecular forces. And then in a solid, those forces are very strong because now it's rigid, right? So it's completely static. So here you've got very, very strong intermolecular forces. So the intermolecular forces here are getting stronger down a cooling curve. And if you go up on a heating curve, so from solid to gas, those forces are getting weaker. Okay. Now let's actually go on to answer the question. So the first question is they ask us to name the phase change between time t0 and t1. Oh, the phase of the substance. Sorry, not the phase change. The phase, okay? So there's T0, there is T1. We've already, from looking at the graph, have said that that space here, it is a gas, okay, for the cooling curve. Let me erase the heating curve, because that's going to confuse you guys. So we've said here, this is a gas, okay? So that is a gas. Then they say, write down the freezing point of this substance. So we've already said that the freezing point is here, this 5 degrees. Okay? 5 degrees Celsius. Then they say, name the process taking place between time t1 and time t2. So here, we've said there's a phase change between a gas and a liquid. What is the name of a phase change from gas to liquid? Yes, 5 degrees is the melting point and the freezing point. And yes, Anati, you're right, it's condensation. Okay, very good. Okay, so here we have, see, let me write this. Condensation. Okay. Use kinetic molecular theory to explain this process. Okay. Whenever something asks you to use kinetic molecular theory to explain anything, kinetic molecular theory is that definition of temperature that we wrote earlier. Okay. It means that temperature is equal to the energy of the particles. Okay. So a gas, to word this question correctly, a gas is a high temperature high energy state. Okay, so that would be the first sentence you have to write. Your next sentence would be a liquid has lower temperature and lower kinetic energy sorry if scrolling is disturbing for anyone, and lower kinetic energy than a gas. Therefore, to go from a solid, or you can even put, if you want to word this really nicely, to condense from a gas to a liquid, energy is lost from the particles of the substance. I can't put the word substance in here now. Okay. Woohoo! Yes, condensation in all caps. You are very excited about that. Okay. Is that explanation of condensation in terms of the kinetic molecular theory clear to everyone? Otherwise, I can try and say it a different way. Okay, great. Okay, then they ask you, after time 3, I've written all over it, but time 3 is there. In what state of matter is this substance? Okay, this is a little bit of a trick question because you can see that on the graph they've given you here, the phase change, all right? So it's not in either phase. It's neither a solid nor a liquid. It's both. There is liquid and solid present in this same vessel. Okay, so there is liquid and solid form of this um, substance present. Because it's still in the process of freezing, okay? If you've ever put an ice tray in the freezer, um, you know that it doesn't immediately, the second you put it in the freezer, go from being liquid water to solid ice, right? When you put the ice in the freezer, it takes a bit of time. And if you come back after about an hour, you'll see there's a little tiny bit of solid on the top, right? But you can break through that quite easily with your finger because it's very, very thin. So, and underneath that, there's water again. So there is solid and liquid present after time 3. Okay, because we are still busy forming the solid that we're going to find here on this bit that we drew in. Okay, it's no longer just liquid. We've gotten too cold for it just to be liquid. So we're here in this liquid to solid transition state, which means that there's going to be both liquid and solid in that same vessel. Does that make sense? I'm going to go back to the kinetic molecular theory question quickly. Okay. So kinetic molecular theory says that all molecules are moving, but the speed at which they are moving depends on their temperature. Okay? So the warmer some molecules get, the more they move. Okay? So it's like me on a winter's day. The warmer I am, the more happy I am to get out of bed and get moving. Okay? Where if it's very, very cold, I'm going to stay in bed and I'm not going to move very much. So, by that theory, a gas, which is where it's very warm, these molecules are moving very, very fast. So they have quite a lot of energy and they're not sticking together really. They're moving too fast to make a intermolecular interaction with their neighbor. They're moving much too fast. Where a liquid is slightly cooler, and it's just cool enough that those molecules are hanging on to each other a little bit. Okay. So that is not what you're going to write in a paper, but that's just a way that I can explain it that makes a bit more sense, hopefully. Okay. Great. Then if we're clear on those two questions, I'm going to move on to 2.2. All right. This is a bit of a trick question because it has a lot to do with wording. All right. So they say, consider the following statements and answer the questions. Boiling is the same as evaporation due to an associated phase change. And then 2, evaporation and boiling have the same phase change, but boiling occurs at a specific temperature. And here they are very nice to you. They actually give you the hint. They ask you to define the boiling point. Okay? And we said that that is the temperature. It's a specific temperature, and there's your hint. It's a specific temperature. Oh, temperature where the vapor pressure equals the atmospheric pressure. Okay. But the very important part of that definition is this bit, that it occurs at a specific temperature. Okay. Evaporation can occur at any temperature. If I put a glass of water or a cup of tea, for example, on a table, and I leave it there for a couple of days, you'll see that there is less water in that cup than there was when I put it down. Okay? And that is because it's been evaporating. But you know, like right now, it is not 100 degrees Celsius, which is the boiling point of water. It is very cold. It's only like 15, 20 degrees during the day. So, but that water is still evaporating. Okay? So that is the difference between evaporation and boiling. Both of them are going from a liquid to a gas. But boiling point, as they say here, occurs at that specific temperature. Okay. So here you would say 2 is correct. Evaporation can occur at any temperature, but boiling is at a specific temperature. Okay. Yes, 2 and 2. Folks who can't see my full screen, it's because I'm zooming in and out. All right, I will zoom out and let you take a screenshot of the question at the end once we're done with that question, which is now. So you can take a couple of seconds, take screenshots if you need, and then we'll move on. Okay. Okay, I hope you've all taken your screenshots because we're going to go on to the next question. Everyone's favorite, stoichiometry. All right. And all of stoichiometry is based on this definition or this law the law of the conservation of mass, which says matter cannot be created or destroyed, but it is transformed from one form to another. Okay? So what that means is if you have on one side of a chemical equation, for argument's sake, 100 grams of stuff, you should, on the other side of that chemical equation, also have 100 grams of stuff. Okay? Which sounds very simple, but we'll get into the nitty-gritty of it in a second. But first, they say to you, study the following processes and answer the questions that follow. Okay? Let's look at these processes before we start answering the questions. Okay? On this reagent side of A, we have solid water. Okay? And on the product side, we have gaseous water. So ice on the reagent side and steam on the product side. All right. Then, let me just get a color. For B, we have carbon and we have oxygen on the reagent side. And on the product side, we have a completely new substance that I'm going to highlight in orange, carbon dioxide. That is a gas. Okay. So, carbon dioxide is a colorless gas that we very commonly find in the atmosphere. It's the gas that you breathe when you breathe out, right? Now, can you tell me, is carbon dioxide the same as the element carbon? Just a yes or no in the chat. Let's see what the votes say. No, no, no. Okay, great, amazing, fantastic. No, it is definitely not. The element carbon is an organic, we call it an organic element, or it's involved in organics. It can be diamond or graphite, but it is definitely not carbon dioxide. It's not the same thing. Neither of these are carbon dioxide, okay? Carbon dioxide is a completely different chemical. Okay, so now 3.1.1, they say identify the process that represents a chemical change. Okay, so just put A or B in the chat. Oh my word. The person who's asked to repeat the question, I'm so sorry, I am not going to be able to pronounce your name, but we're asking which process is a chemical reaction or a chemical process, and which one is a physical process. So which one's a chemical process? I'm seeing a lot of B, and you are correct. B, correct. Okay, this is the chemical reaction, B. Okay, so it is B. And then obviously the one that is a physical change has to be A. Okay. Are the above processes endothermic or exothermic? And provide a reason. All right. So let's quickly go over what the difference is between endo and exothermic. Endo is like an entrance. So enter or an entrance, right? And exo is like an exit. Okay. Thermic refers to temperature. So this is temperature. Okay. So, or heat is another way to say it. So it's temperature or heat. Okay. So for an endothermic process, heat enters that process. Okay. And for an exothermic, heat leaves the process. Okay. If you look at these two processes, is heat entering or leaving them? Oh, Dina's on a roll. Yes, they're exothermic. Okay. No, they're endothermic. Sorry. They're endothermic. Both of these processes are endothermic. Yes. Heat is entering these processes. You are adding heat. Okay. You're adding heat to these processes to make them happen. So they are very much endothermic. Okay. So that's the answer. They're endothermic. Okay. And the reason for their answer is that you're adding heat. Okay. You're having to add heat to make these processes go to completion. Okay. Going on to some naming of compounds. Okay, when is heat released? Okay, so they would not normally, at your level, I don't think you're going to see a delta H. Maybe you will. Um, so if heat is being released, okay, for example, I'm trying to think of a process that gives off heat. Iron and sulfur. When you react them, they form iron sulfide. Um, and this releases heat. So it'll be written like this, okay? When you're adding heat, it's either written on the reagent side, so it's either written here or on top of the arrow if you're adding heat. If you're losing heat or heat is exiting this process, it'll be written on the product side. Okay. Dina, you say you don't understand. Okay. So let me try and explain this to you in a way that is slightly differently worded. Okay. So an endothermic process, you need to add heat. Heat needs to enter as a reagent, in a manner of speaking. Okay? Exothermic, heat is leaving that process. So you are having heat as one of the products of your reaction. Okay? When heat is written on top of the arrow like this, it means that you are adding heat. Okay? So, for example, melting ice, you have to add heat. Okay? Not necessarily in the sense that you might be thinking, which is like holding it in a flame, but some heat is being added because of the environment. Okay, there's heat from the environment going into this process. Is that a bit clearer? Okay. The session, I believe, is supposed to end at 8, but we might go a little bit over time just because we are taking a bit long to get through the paper. Okay. Uh, okay. Here they're asking you to name the following compounds. Okay. So when they say naming a compound, they are not referring to the common name of a compound. They're referring to the scientific name. Okay. Okay. The common name for this compound would be bromic acid, but the scientific name for it we're going to get by looking at the two constituent elements. All right. So, what element is Br? Quickly in the chat. Woohoo! Yes, hydrogen bromide. Okay, some people are on a ball. Okay, yes. Okay, I'm glad you see that bromine is Br, boron is B. Okay, so this is hydrogen bromide. This is why it's important to learn the symbols for some common elements. All right. The next one, we have carbon and we have chlorine, but we have 4 chlorines. Do you see? There, that 4. Okay. So because this is a covalent substance, it's a non-metal and a non-metal, the number of chlorines becomes significant. Okay. So in chemistry, we really like Greek numbers. Okay. So 1 in Greek is mono. 2 in Greek is di. 3 is tri. And 4 is tetra. Okay. And then after that, there's the ones that you might be familiar with from geometry, like penta and hexa. Okay. But we are looking at 4, which is tetra. So here we're going to say carbon. There's 4, so tetra. And this is chlorine, so chloride. Everyone happy? Yes, carbon tetrachloride. Oh, you guys are on an absolute ball with the naming of compounds. Okay. The last one, does anyone know the name of this polyatomic ion? Okay. Let's see if anyone's absolutely on the ball with the name of that polyatomic ion. Let me put it back on the screen quickly. Okay, it is not sulfate. Sulfate is SO4. Sulfate looks like this. Does anyone know that one? Trioxide? Oxide? Nope. Okay. So I think this has been removed from the syllabus, but for interest, this is a polyatomic ion called thiosaphate. Okay. So this would be, coming down from here, sodium thiosaphate. Don't stress too much if you don't know the name of this polyatomic ion. It's very, very rarely asked, and I actually think it has been removed from the syllabus. All right. Okay. Now we get into the nitty-gritty. Balancing some reactions. Okay. I'm going to do the first one with you, and then I'm going to give you one to try on your own and put your answers in the chat. So let's start with this. Okay. So we have iron and we have oxygen, and they are combining to make iron oxide. Okay. This is rust. Okay. The weird red-brown stuff that forms if you leave something iron outside for too long. So when you're balancing a reaction, you can kind of think of it like an old-timey, like these balance scales that you used to see in the olden days. It kind of works like this, okay? Because we're working with the law of conservation of mass. So on the reactant side, which is one little basket, okay, we have some iron and we have some oxygen. And on the product side, which is the other little basket, we also have some iron and some oxygen. But now they have to match up, right? Because we want this scale to be balanced. We don't want it to be tipping one way or the other, because then we're not following that law of conservation of mass. All right. So on the product side, we currently have 2 iron atoms and 3 oxygen atoms. On the reagent side, we currently have 2 oxygen atoms and 1 iron atom. Okay. We can immediately see this as a problem. So what is, and this is going to throw you back to maths, the lowest common multiple of 2 and 3? Six. Yes, great. Okay. Woohoo! No, not the common factor, the common multiple. Okay, 6. Okay, so Here, to make 6, we need to multiply this product side by 2. So here we have a 2. And we need to multiply the reagent side by 3. All right. So that balances our oxygen because now we have 6 and 6. But by doing that, we've upset the balance for, well, it wasn't balanced to begin with, but now we have 4 iron here on the product side. So on this side, we now need to make 4 iron, but that's easy because we can just put a 4 up front here and it's all nice and balanced. All right. So do the next question by yourselves. I'm going to give you guys 5 minutes and then put your answers in the chat. 4 from where? Okay. So there's a little 2 here. Okay. So that means for every unit of rust that we have, there are 2 iron atoms. So if we multiply rust by 2, we get 4. Okay, so it's always the big number in front times this little number. Okay, so that's how we got 6. We got 2 times 3, and that's how we got 4 iron. We had 2 by 2. Okay, have a look at this question with the carbons, the hydrogens, and the oxygens. One more minute. Let's see if there are some answers. Woohoo! Okay. I'm seeing some 2 carbon dioxide and 6 and 3 water. Okay. Uh, okay, you're on the right track. And okay, let's go over this because it looks like you guys are mostly on the right track. All right. So you have carbon, hydrogen, and oxygen, and you have carbon, hydrogen, and oxygen. Now, when you're doing a balancing question, I recommend you start with everything that is not hydrogen and not oxygen. So in this case, start with carbon, okay? On this side, you have 2 carbons. Okay, let's do this in another color, 2. And on this side, you only have the 1. So the first thing that you're going to need to do is you're going to need to multiply the carbon dioxide on the product side by 2, right? Okay, now that's balanced. Happy days. But what does that do to the oxygen? Okay, so here someone was asking me earlier, where did I get the 4 from? You're going to multiply the stoichiometric coefficient by these little numbers inside. So the ratio of atoms in the compound. Okay. So 2 times 2 gives me 4. So there's 4 there. And there's another one here. Okay. So easy mistake to make to miss this one. So there are 5 oxygens here right now. Okay. And how many are there on this side? There are only 2. Okay, that's no good. So now we can start looking at balancing. Let's start with a hydrogen, actually, because on this side, you have 2 hydrogen, and on this side, you have 6. Okay, that's a heck of a lot of hydrogen compared to 2. So, divide by 3. Okay, because now I have 6 and 6. But that still doesn't solve the oxygen problem. Okay, because now how many oxygens are on this side? I still have the 4 from the carbon dioxide, and now I add another 3, so that's 7. Okay, that's still no good. All right, but do you notice this oxygen here is diatomic? It's multiplying itself by 2, which means on this reagent side of this equation, I am only ever going to have an even number of oxygens. Okay, so what is the easiest way to get both 2 here and 3 here to turn into even numbers? Okay, 2 is already an even number, but we're going to multiply here by 2. All right. Okay, so by 2 again. So 6. Okay, so a lot of you got to the step where you had 2 carbon dioxide and 3 water, but you should have picked up that that doesn't balance your oxygen. Okay, so now I have 6 there. Now here I can start fiddling with the oxygen, but it doesn't help for the hydrogen. Okay, so right now, as it stands, I have, sorry, let's get a pen. I have 6 oxygen coming from here, and I have another 4 coming from there. So I have 10. Okay. Now I can solve that from this diatomic molecule and put a 5 in front of it. Okay, so now I have 10 and 10, so they match up. But now the hydrogens are upset again because I have 12 hydrogens there. That's no good because I only have 6 on this side. So I need to make that 12. And I'm going to do that by multiplying this whole situation by 2. So now I have 12. But now that's given me 4 carbons. So how am I going to solve that? I'm going to put another 4 carbons. So I'm going to put 4 there. That makes 4 carbons. And the last little bit of fiddling that we have to do. Everything is solved except the oxygen now. Okay? Because this is 4 and 2, that's 8. And this is 6. So 8 plus 6 is 14. Okay? So how do we get 14 from 2? We multiply it by 7. And that gives me 14. So that is your final balanced equation. That was a very tough one. So well done to everybody who got to that step with the 2 and the 3. And if anybody did get further but wasn't feeling brave, well done to you too. Okay. The 5 oxygen. I'm guessing that was earlier where I had the 2 in front of the carbon dioxide. Remember that when you are adding the number for the balancing down here, you have to multiply the stoichiometric coefficient by the ratio. Okay, so there are 2 oxygens for every carbon dioxide. So if you put 4 carbon dioxides, that will give you 8 oxygen. And remember, there's another oxygen in the water. So you have to add all of those oxygens up. Okay, that should answer where the 5 oxygens were coming from. Okay, that was a bit of a scary balancing question. The next one is not so bad. Okay. The next one just involves some polyatomic ions. Okay, we saw a polyatomic ion earlier, the sodium thiosulfate. But let's have a look here what's going on. So there you have sulfate, and there you have sulfate. And here you have nitrate, and there you have nitrate. All right. When you are doing a balancing question with polyatomic ions, NB, 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 do not mess with what is in those ions, okay? Do not mess with the number of sulfurs, okay? Do not mess with the number of nitrogens. Treat the whole ion as one thing to balance, okay? Because the composition of these ions has not changed. It's SO4 on the product side, it's SO4 on the reactant side. So just leave them alone, okay? So work with them as SO4 and NO3 as a whole unit like this, okay? And then you have your sodium and you have your barium. All right. So the first thing to note, there is this 2 here. So there are 2 nitrate groups on the reagent side. 2. So to balance, we are going to put a 2 in front of that sodium nitrate, this whole compound. Okay. Oh, sorry. I've written Na and Ba. It should be Na Na and Ba Ba. Sorry if that confused anyone. Okay. So let me start again. We have 2 nitrate groups on the reagent side. So to balance that, on the product side, I multiplied this sodium nitrate by 2. Okay, now our nitrates are balanced. But now our sodium is unbalanced. Well, it actually balances itself because now we have 2 sodiums there. And if we go back to the reagent side, there's already 2 sodium on the reagent side. And all the rest is just 1 and 1 and 1 and 1. So that was very, very quick and easy to balance. The trick there is not to get super focused on the elements, but rather to work with the polyatomic ions as one unit. Okay. Then, for the next question. Wait, before I move on, let me check if everyone doing okay? Was that clear? Okay. Please repeat how to work with the ions. Okay. So, you should, from the beginning of the year, know that this is a sulfate group and this is a nitrate group. Okay? You should know those. You should recognize them when you see them. Okay? This is a nitrate, that is a sulfate. Immediately when you see them, you should know. So, when you see a polyatomic ion, so a nitrate or a sulfate or a phosphate or a nitrite or a hydroxide, any of those polyatomic ions that you learned, you should immediately know that this is an inseparable unit. You don't try and separate this out into nitrogen and oxygen and balance them separately. No, you work with them as one. It's a nitrate. Just deal with it as a nitrate. Okay. You understand? Okay, you understand the ions, but what don't you get? How to balance? Okay. So, when you see polyatomic ions and you need to balance them, here are your nitrates. Okay, they're in green. And here are your sulfates. They're in blue. So you deal with them as a unit. Oopsie. You're going to deal with them as a unit. I'm going to redo this question for you. Okay. When you have a sulfate and a nitrate, you deal with that ion as one whole thing. Okay. So on this side, you have 2 nitrate ions. 2. On this side, you only have the 1. So the easiest way to get them to balance is to put a 2 in front of this sodium nitrate salt. Okay, so that gives you then 2 there. And at the same time, it's solving a problem that you haven't even looked at, which is that right in the beginning, there are 2 sodiums on the reagent side. So you started out with 2 here, and now by doing this, you also have 2 there. And that's it. Your reagent, your whole equation is balanced. What would happen if you dealt with the nitrate and the sulfate as separate atoms? Dina, you would have, it would work, but it would be absolutely horrible because you would end up dealing with so many different atoms that you have to watch out for. Okay, so it is always just much easier to deal with your polyatomic ions as one thing. Okay. Hope that answers that. Question 3.4. They ask you to state the law of conservation of mass, which we've already done way back at the beginning. It's that matter cannot be created or destroyed, but is transformed from one form to another. Okay, that's the law of conservation of mass. And then they want you to show that this reaction here, oh my word, that's a very skinny line, obeys the law of conservation of mass. So how do we do this? When you are doing a proof, okay, you cannot write an equal sign in the middle of two bits of the proof, all right? You need to prove this side is equal to something, and then you work out that side, and they should be equal to the same thing, okay? But you cannot say that one side equals the other side from the beginning. It does not work like that. You are proving it, okay? So on the reagent side, you have 2 HNO3 plus 1 calcium hydroxide, all right? So when you take the molar mass of each of these, you can find that on your periodic table, okay? Hydrogen has a molar mass of 1, nitrogen has a molar mass of 14, oxygen has a molar mass of 16, okay? And all of this you multiply by 2. You add that to calcium has a molar mass of 40, oxygen we've said is 16, and hydrogen we've said is 1. When you add all of this together, you can put it into your calculator. It gives you 160 grams per mole. Okay, so that is the reagents. Okay, now we do the products. And the products are calcium nitrate. So calcium, we've said molar mass 40 plus 2. Nitrogen, we've said is 14. And oxygen, we've said is 16. Okay, so I'm just taking molar masses. They're on the periodic table. Okay, what is the AQ? I will come back and explain that. And yes, I should definitely charge my tablet. Thank you for the reminder so that it doesn't die on us. Okay, there we go. We are charging. All right. So on the product side, we have the calcium plus the nitrate. Okay, and we have the water. So it's 2, and then 1 plus 1 plus 60. Okay, and that also, when you put it into your calculator, gives you 160 grams per mole. Because the molar mass, okay, remember molar mass you write as a capital M, of the reagents equals the molar mass of the products. Therefore, it obeys. Okay. The question about the AQ and the H and the Ls, sorry. Okay. All of these are just phase symbols. Okay. So AQ just means dissolved in water. All right. And L just means liquid. Okay. So AQ stands for aqueous, and I cannot spell that word to save my life. Aqueous, I think. Okay. So that's what AQ stands for. All right. Is everyone happy with the proof of molar masses? Reagents are the reactants? Yes, it's all the same thing. Okay. Reagents, reactants, it's the same. Okay. Can I get a screenshot? Yes, you absolutely can. I'm going to zoom out so you can all take a screenshot quickly. There we go. Okay, well, I'm going to try fit it all on one page, but it's getting a bit small now. There we go. Okay. Hope you've taken your screenshots because we're going to go on to question 4. Okay. So I've split question 4 into 2 parts because that's how they've split it in the second as well. Question 4 deals with isotopes, which are atoms of the same element with a different number of neutrons. Okay. So when they say of the same element, this bit that I'm going to highlight in pink, okay, that means that they have the same number of protons. Okay. They do not necessarily have the same number of electrons, but they have to have the same number of protons. Okay. The number of protons is what makes something the element that it is. If you are changing your number of protons, you are no longer the same element. Okay. Now, neutrons are neutral in their charge. Okay. So they have the notation N neutral. Okay. Now, if we make a quick table here, let me just get some color that you'll be able to see here. Okay. If we make a table of neutrons, protons, and electrons, and we compare their mass and their charge, okay? Oops. Okay. Neutrons have 1 atomic mass unit, okay? Protons are 1 atomic mass unit. Electrons are teeny, teeny, tiny. They have basically no mass, okay? They do, but it's like 10 to the negative 30 something. So it doesn't matter. You can say more or less 0 atomic mass units. Okay? A neutron has a 0 charge, a proton has a positive charge, and an electron has a negative charge. Okay. So when you are looking at the mass of something, the 2 things that contribute to the mass are going to be the neutrons and the protons. The electrons you can practically ignore. Okay. So here we go. They're talking about magnesium and its 3 naturally occurring isotopes. Okay. Magnesium 24, magnesium 25, and magnesium 26. The first question is name the group in which magnesium is found. Let's start there. Answers in the chat. Name of the group. Okay, the name. So yes, 2 is the right number, but what is the name of group 2? Okay, so you guys are right. It is a group 2, but group 2 has a name. Okay, alkali, but alkali what? Alkali earth. Yes. Okay. So magnesium is an alkali earth metal. Okay. Okay. Then they ask you about the element that has the same number of electrons as there are core electrons in magnesium. Okay. So let's actually draw magnesium's electron configuration, okay? Because they're going to ask about it just now anyway. Okay. So I'm not too worried about what's going on in the nucleus. Suffice to say it's positively charged. Right. Now, magnesium is in period 3. So it has 3 electron shells, okay? Which means that its electron shell 1 and 2 are completely full, okay? They are chock-a-block. Like when you go to a hotel and they tell you we have no more room, it's like that. There is no more room for electrons on the first and second shell of magnesium, okay? So 1s, which is the first shell, is full. Oopsie, I missed 2s. Okay. The next orbital is 2s, which is the first orbital in shell 2. Okay. After 2s comes 2p, and that is also full. All 6 electrons are there in 2p. Okay. Now we get to where magnesium becomes interesting. It's shell 3. So this is 1s, this is 2s, this is 2p. Okay. On shell 3, magnesium has only 2 electrons. Okay. So the core electrons of magnesium are everything up until 2p. Okay. So which element? Yes, I do believe you do tomorrow physics, but I'm not teaching that. Okay. So which element on the periodic table, look at your periodic table, has a full 2p orbital and nothing in the 3s orbital? So if you want to count out these electrons, there will be 10. Okay, there's 10 electrons, core electrons. Okay, so which element has 10 core electrons? Yo, guys, there's a lot of you that, okay, there we go. Yes, it's neon. 10 core electrons is neon. All right. Helium has 2 electrons, not 10. All right. Oops, 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 oops. There we go. Okay. So yes, it's neon. Okay. Then they say, calculate the number of neutrons in magnesium 26. So if we go back up to this table that we drew, which two contribute to mass? We said it was neutrons and protons. Okay, so the number of neutrons in magnesium 26 is going to be 26, which is the mass, minus the number of, okay, so let's do this. The number of neutrons is equal to 26 minus the number of protons. How many protons does magnesium have? Quickly, put your answers in the chat. How many protons in magnesium? 12, yes. Okay, so the number of protons is 12, so that's just going to give you 14 neutrons. Ah, sorry. Neutrons. Okay. Now, they say calculate the percentage abundance of two. You know that percentages, any percentages, must always add up to 100. So when you say 100 minus the sum of those, it gives you 10%. Okay. That's something you will know from primary school maths. Okay, so it's 10%. Then they ask for the relative atomic mass of magnesium. Okay, and this is the tricky bit of this question. Relative atomic mass, okay, is the sum of the percentage abundance of each isotope and that isotope mass, all divided by 100. Okay. Now, if this formula doesn't make a whole lot of sense to you, don't worry. I'm going to explain it with magnesium now. Okay. What you are doing is taking what is called a weighted average. Okay. So when you get this table, you're going to look at the isotope mass and its percentage abundance. Okay. So the isotope mass here is 23.985. So 24. Okay. So we are going to multiply this percentage abundance by the atomic mass. Okay. So we're going to say 78.99% or 78.99. Let's just go like that. 78.99 times 23.985 plus. Okay, so that's one isotope done. Now we go on to the next isotope. 24.959. Sorry, I'm doing this in the wrong order. So it would be the, doesn't really matter because you're multiplying, but so it would be 10 times 24.959 and space. And then the last isotope we need to do is 11.01 times 25.983. Okay? And then we divide all of that by 100. Okay? So all that you're doing is taking each isotope one at a time. You are multiplying its percentage abundance by its atomic mass, and then you are adding up those terms. Okay. And this, when you put it into your calculator, gives you 24.302 grams per mole. Okay. That is that, and I see it is nearly 8 o'clock. So for those of you who are only staying till 8 o'clock or are in a rush to get somewhere, have another appointment, the rest of this will be recorded, but I'm going to go slightly over time because I do want to go over, yes, 3 decimal places because one of them is a 0. You don't count a 0 when you're counting out the number of decimal places. Okay. Another reason you can say that it has to be 3 decimal places is because that's what they've given you in the question. Okay. There, there, there are 3 decimal places. Okay. If you had put 2, you would only lose half a mark. All right. So I'm going to go on to the next question. Those of you who need to be somewhere else, feel free to watch the recording. Okay. This next question is quite quick. It's about electrons and diatomic elements. Okay. So Pauli's exclusion principle is one of the fundamental principles of chemistry. It says that there are a maximum of 2 electrons in an orbital, provided that they spin in opposite directions. Okay. And you'll see why that comes back in a second. The first question is oxygen exists naturally as a diatomic molecule. What is that? It's a molecule that consists of two atoms of the same element. Okay? So oxygen occurs like this, nitrogen occurs like this, all your halides exist like this. Quite a lot of the gases exist as diatomic molecules. Okay. Then they say, give the valency of oxygen in its natural state. Okay. So what they're talking about with valency is the difference between the number of electrons on an atom and either 0 or 8. Okay. So you're either going to 0 or going to 8. Okay. So whatever the number of atoms, electrons on your atom is, you put that in the middle. Okay. So here we have 6. Is 6 closer to 0 or closer to 8? Oh, yes, I'll go back and let you screenshot the next question in a second. Sorry. Okay. 6 is closer to 8. All right. It's going this way. And the difference is 2. Okay. So that is the valency of oxygen. The valency of oxygen in its natural state is 2. Okay. Simmer over that for a second, and I'm going to let you take a nice screenshot of this question here. I give you a couple of seconds. Okay. Let's go back. Then they say, write down the electronic configuration for the oxygen atom. All right. Now I'm going to do the same thing that I did for magnesium earlier, and I'm actually going to draw it. You do not have to draw it to answer this question. It's just easier to teach if I draw it. Okay. So the first orbital is 1s, which can take 2 electrons. Oxygen is way past having 2 electrons, so that is full. The next orbital, so that's 1s. Okay. The next orbital is 2s, which can also take 2 electrons. This is still less electrons than oxygen currently has. Okay. There. So that is 2s. Okay. The next shell, or the next orbital that we're looking at, is 2p. Now 2p can take 6 electrons. But oxygen only has 8 electrons in total. So it's only going to fill, so it already has filled 1, 2, 3, 4. It can only put in another 4 electrons, and then it's done. That's all it has. Okay? So it is going to put 1, 2, 3, and 4 into 2p. Okay? So now, if we had to write this, okay, which is what they're asking us to do here, it goes like this. 1s has 2 inside. 2s also has 2 inside. And 2p has 4. Okay. Is it clear to everyone how I got there? Yes, Dina, when you were stating the valency of an atom, you're just saying that difference. So it's either 2, 3, 4. It's not necessarily, it's not with the charge. -2 is its charge, not its valency. Okay. It's a matter of semantics. A lot of chemists get those words confused, but it is valency is just 2 the charge would be -2. Okay. I saw someone asked where to find the recording. It is on the YouTube channel of the Learning Space. Okay. Name the type of bonding that takes place in the oxygen molecule. Okay. So oxygen is a nonmetal bonding to another oxygen, which is another nonmetal. So that is, you guys were saying it earlier, it's a covalent bond. Okay. That looks like an emoji. Okay. You are welcome to take a screenshot here, and then I'll go on to the next question. Okay, I hope everyone's taken their screenshots. We're going to move on to question 5, which is luckily quite quick. Okay. It's on bonding and Lewis structures. So the first thing they ask you is to give the definition of an ionic bond. It's a chemical bond in which, I see I made a typo, in which or whereby electrons are transferred from one atom to another, okay? So they form ions and then subsequently attract one another, okay? Then we need to draw some Lewis structures. So I'm going to start with 5.2.1, which is carbon dioxide. So we have carbon and we have oxygen and we have another oxygen. Where Okay, we have carbon and we have oxygen. Okay, so like earlier, I'm going to do carbon in pink. Carbon has 1, 2, 3, 4 electrons in its valence shell. Oxygen has 2, 4, 6 in its valence shell. 2, 4, and 6. Okay. For a Lewis diagram, you can draw them as crosses or as circles. It doesn't matter. But yeah, they're going to look like this. Then the next step is that each of these is going to arrange its electrons such that it has the 2 bonding electrons, so this carbon with this oxygen, are going to form a bond like so. Okay? And this oxygen is going to bond in on this side. But can you see we do have a problem? The problem is there, 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 and there. We have these extra electrons just hanging around. All right. So what they will do is they will form double bonds. Okay. So carbon is going to arrange its atoms like this, or its electrons, my apologies. And then oxygen is going to arrange its electrons like that. Okay. The lone pairs on oxygen are going to arrange themselves at an angle like this. And that's your final molecule. So what they are giving you marks for is that you still have lone pairs on both your oxygens. So those lone pairs are 1 mark, and the double bonds in the middle are another mark, because this is for 2 marks. Okay. Yes. Okay. It is absolutely important that you have the elements in the correct order. Okay. And the reason for that, Dina, is if I had carbon, oxygen, and oxygen, okay, for example, this does not happen, but let's, for argument's sake, say it does. I would have carbon here with its 2 electrons, making a double bond with that oxygen. Maybe this oxygen would arrange its electrons like this. But now, do you see we have a problem? Because it has no electrons here to share with this oxygen. Okay. Maybe if you were doing it this way, you would say, okay, well, then leave that one there for carbon and do this. And then do that. And but okay, wait, let me make this another color so that's easier to see what I'm doing. Okay. So you have this set up. Then you see you have all these electrons that have nowhere to go. There's this electron that has nowhere to go. There's all 3 of these electrons that have nowhere to go. So you'd have a massive problem doing this, okay? You would have literally nowhere to put these and that electron. So that's why the order matters. Okay. Carbon dioxide is one of those that is useful to learn because they love to ask it. Okay. How do you know how to arrange them? Okay. So if you had this arrangement, okay, then you would maybe see that, okay, well, I have 3 electrons there and I have 1 there. So that will give me an even number. That'll still give me some sort of pairing structure, right? So you would move this oxygen there and have an electron from the carbon. And now at least you have a pair on carbon, a pair bonding. Okay, so you're already in a much better situation than you were a couple of seconds ago with this oxygen setup. Okay. But then you would have to remember that carbon and oxygen can both make double bonds. It is unfortunately just something that you have to know. Is carbon and oxygen both make double bonds when they're in this sort of situation that I'm depicting down here, which is with the electrons getting stuck, okay, on the outside. They would rather then bring this electron in here and make a double bond, okay? Sorry, let me just, no, okay. So you would have to know that that is just, it's a property of carbon and of oxygen. Unfortunately, you just have to know it, okay? I'm going to erase all the stuff that's incorrect. And then we can move on to ammonia, unless there's a question about that in the chat. Okay. So I'm going to move on to ammonia. Nitrogen we find in group 5, or well, group 15, 5, same thing, on the periodic table. Okay? Which means that it has 5 electrons in the valence shell. Let me make them a color so we can see. 2, 3, 4, and 5. Okay. Hydrogen only has 1 electron. And they're being really, really nice to you here. They're giving you these elements in the right ratios. Sometimes they'll just ask, okay, we'll draw the bond between X and Y, right? So all our hydrogens just have 1 electron each. So the most efficient way for your hydrogens to arrange themselves around this nitrogen are to share this electron over here, to share this electron over there, and that electron over there. Okay, they're not exchanging, they're sharing. Okay, it's covalent. So nitrogen still looks the same. It's pulled the hydrogens nice and close to itself so it can share their electrons. And it's going to look like this. Okay, that's the whole of question 5. It's very short and sweet. You're welcome to take a screenshot. Okay, has everyone who wanted one taken a screenshot? I hope so. Okay. This is maybe the last question I'll do with you now, but I'm going to skip all the stuff that's memorizing, okay? Because some of this is just memorizing, unfortunately. Okay. The definition that they ask for in this question is the definition of an aqueous solution. So that is, I know someone was asking earlier, what is the symbol AQ? It means aqueous solution, a solution where water is used as the solvent, okay? So they give you these two reactions here, okay? So they're saying, well, into the one test tube, they've put sodium carbonate, and in the other one, they've put sodium sulfate, okay? So this is Na2CO3, and this is Na2SO4. Okay, oh, they've given it to you here. And they add barium chloride to both. And in both of these test tubes, there is some white solid that forms. Okay. Now, they ask what type of reaction that is. It's a precipitation reaction. When there's a white solid or any solid forming out of a solution, it's precipitation. Okay. Then they say, write down the chemical formula of the salt produced in test tube A. Okay. So, both of these are aqueous, but there's going to be a salt that forms. A salt is something that can redissolve. Okay, so the barium is going to bond to the carbonate, and you're going to end up with sodium and chloride left in the solution. Okay, because barium carbonates are insoluble in water. Okay. So barium carbonate is going to be this white solid, and it's going to be the chlorine and the sodium that are going to be a salt, i.e. they're going to redissolve. Okay. They ask for the name of it. Oh, no, they don't. Not in this question. Oh, sorry. Yeah. So there's going to be NaCl and then the barium carbonate. 3. So both of those are going to form. Okay. Now they say nitric acid, HNO3, is added to both the test tubes. Okay. Now here, you need to remember something. Okay. They're adding nitric acid, HNO3. Okay. The salts that you have are barium carbonate, okay, because the NaCl has redissolved. So the precipitates are barium carbonate and barium sulfate. Okay. When you react any acid, and a carbonate, okay, you will get carbon dioxide, water, and a salt. Okay, that is a rule that you have to know. But reacting an acid with a sulfate doesn't do anything. Okay, it doesn't go anywhere. So when you are forming carbon dioxide, water, and a salt, the salt will redissolve. The carbon dioxide is a gas, and this whole thing is dissolved in water already. So this is going to just disappear. Okay. So nothing is going to change in test tube B, where you're adding the acid to the sulfate. Nothing is going to change. Okay? These are not going to react in any way that you can see with your eyes. Okay? So here, there's no change. But where you're reacting the acid with the carbonate, you're getting a gas, water, and a soluble product. So your precipitate, which is this, is going to appear to redissolve. Okay, because all of this is going to seem to just disappear. Okay, so the precipitate dissolves. That's the change that you're going to see. Okay. Then they say write down the balanced reaction that explains the observation in 6.4. Okay, so this is the bit that they're asking you to show. So it's barium carbonate plus HNO3 is going to give you barium nitrate plus carbon dioxide plus water. Okay. Now, barium carries barium carbonate. Yeah. So this, okay, let me explain. Okay. Carbonate is a 2 minus ion. So barium, also if you look at where it is on the periodic table, is a 2 plus ion. Okay. It's in group 2, so it's a 2 plus ion in solution. Okay, hydrogen is a 1 plus, nitrate is a 1 minus. Okay, barium we said has to be 2 plus, this is 1 minus. Okay, so you can see these charges that are up here are not balanced. To balance the charges, I'm going to put a 2 around just the nitrate group. Okay. This is part of knowing how salts recombine. How do you know if a compound is an aqueous solution? Okay, it's dissolving in water. That's the prerequisite. Okay. So if you look at the definition, it's where water is used as solvent. All right. So there are solubility rules I don't know if they're still in the syllabus. If they've been taken out, lucky you, because they are very involved and a lot to remember. But when this was in the paper, it was still in the syllabus, and I think it's still in the syllabus for you as well. Okay. Carbon dioxide and water, we know the compositions of, so that's all good. Now, to balance the nitrate and the hydrogen, I'm going to put 2 in front of the nitric acid. Okay. And the rest, this oxygen here and this oxygen here, make that CO3. There's 1 carbon and there's 1 barium. So all of the rest of that equation is already happening. Okay. That's the end of question 6, so you're welcome to take a screenshot. Is everyone okay with what happened in question 6? You are awfully quiet. Is there anyone still in the chat? Oh yeah, there's a few people. What are you doing? Okay, everyone happy. Good. Almost there. Almost there. Question 7, solutions. A solution is a homogeneous mixture of 2 or more substances. Okay? I personally do not like this definition because this 2 or more substances you can split up into solute and solvent. Okay. The solvent is the medium that everything else is dissolved in. Okay, so water or ethanol, some organic reactions we dissolve in chloroform. Okay, so that's usually a liquid, where the solute is what is dissolving. Okay, it's the bit that's dissolving. And this is normally, not always, but normally a solid. Okay, so this is everything else, basically. Then here, the next definition is an electrolyte, a solution that conducts electricity through the movement of ions. Okay, which is all good and well to say, but what does that actually mean? Okay, so if I have a beaker and I dissolve in it Na plus and Cl minus, and I then put in 2 electrodes, a negative electrode and a positive electrode. Okay. The sodium is going to be attracted to this negative electrode, and the chlorine is going to be attracted to this positive electrode because opposites attract. So there's not just 1 chlorine and 1 sodium in this whole solution, right? There's a lot of chlorine and a lot of sodium. And as these become attracted to their respective, well, let me not draw it like that, to their respective electrodes, there's also charge moving in the solution. And when charge is moving, that is electricity. Okay, so that is how these solutions conduct electricity. So it is always an ionic solute. Okay. If you have an ionic solute, chances are it's an electrolyte. Okay. Here we go. Write down the formula for sodium chloride. That's just NaCl. We've seen that a couple of times in the paper, so I'm not going to elaborate on that. What is its common name? What do we call Anati, is this the last question? There is one more question after this, but I think this is the last question we'll do tonight. Okay. What is the common formula or the common name for sodium chloride? It's in our houses. Yeah, it's salt. It's table salt. Okay. We all know this as table salt or salt. Then they set up this experiment to determine the electrical conductivity of some solutions. Okay. And the solutions that they're talking about here is a solution of sugar and a solution of sodium chloride. So we've said sodium chloride is NaCl. Now, you guys don't know the formula for sugar, but I am telling you for free. It's C6H12O6. Okay, it's glucose. Now, this is ionic, right? We use that as in our example. It's going to dissociate into Na plus and Cl minus. Okay? This is covalent. This cannot dissociate. So this is not going to form an electrolyte. So what physical quantity is measured by component X in this diagram? Okay, so they've thrown a physics question in here, which is fine. This is an ammeter. It measures current. Okay, milliamperes, which is what it's reading there, is a current. Okay. Which solution, A or B, so the sugar or the salt, will give a reading on X and give a reason? Can I hear quickly, sugar or salt? What's giving us a reading on X? Salt? 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 Yeah, it's salt. Okay, salt is that ionic compound. It's going to let the charge move. Okay, so the definition of current, which you know from physics, is rate of flow of charge. Excuse my handwriting, it gets worse as I try and write faster. Okay, so it is going to be B, the salt. B, and here you can say it's an ionic solute and an electrolyte. Okay. Then, quickly, last question for the evening. How would an increase in the concentration of B, so salt, affect the reading on X? Increase, decrease, or stay the same? Answers in the chat, please. Decrease, increase, you don't know, okay? So we're increasing the concentration. Okay. Concentration is number of moles over volume. So another way to think about this is it's the number of atoms or ions in that same space, more or less. Okay, that's not the exact definition, but it's a way to think about it. So if we are increasing the number of ions in that same space, then we are also increasing, if we go back up to this lovely little diagram, we are increasing the number of ions that can interact with either electrode. Okay, so we are increasing this and we're increasing this. So we're having more and more and more and more and more over and over interaction with these electrodes. So there's more and more current that's going to move. Okay. And that is what leads you to the conclusion that when you increase the concentration of an electrolyte, you're going to have an increase in the current. Okay. Because I'm going to just write the shorthand. If you increase the concentration of, let's just go an electrolyte. Okay, when you in chemistry write something in square brackets like this, it means concentration. You are increasing the number of ions, and that is increasing the charge that is flowing. And that is what gives you the increase in the current. Okay. That's the last question for the evening, folks. You're welcome to take a screenshot. Any last minute questions, you're welcome to put into the chat. And then we will sign off and all hopefully go to bed and revise again tomorrow.